Okay, thank you. Okay, so thank you again for being here. My name is Konagaya. I presented 2 slots earlier, and this time I will talk about the supercomputer simulations which our group has conducted about our new reaction principle. And my talk this time is titled Supercomputer Simulation and Experiment Clarifying the Maximum Level of Focusing Compression Due to Pulsed Super Multijets Colliding in Weak Cold Fusion Engine Fusion. So this will be a repetition of what I said before, but we have previously proposed a new principle for generating reactions, which is called focusing compression due to pulsed super multijets colliding for fast chemical reaction in weak cold fusion engine. So in this principle, multiple high-speed gas jets are injected from the sidewalls, colliding at a singular point at the center of the reaction chamber, causing fast chemical and weak nuclear reactions. This new reaction principle will achieve high compression ratio around the collision point, leading to fast chemical reactions of hydrogen and oxygen, and weak cold fusion of hydrogen or deuterium plus palladium, high power and high efficiency, while maintaining relatively silent combustion due to reactions at the chamber center far from the solid wall. And also there will be no heat loss at the chamber wall due to encasing of the reacted gas around the chamber center, increasing heat resistance. So currently we are thinking of 2 basic scenarios for this engine to be used in a weak cold fusion engine. The first type is single focusing collision of H2 or D2 and palladium injected into atmospheric chamber. And the second type of scenario we are thinking is single focusing collision of H2 or D2 and palladium injected in initially heated chamber of about 1,500 K. So we did some simulation, 3-dimensional simulations using a supercomputer. And first I'll talk about the simulation model we used in its evaluation. Firstly, these are governing equations we used. The 3-dimensional unsteady compressible Navier-Stokes equation using the substantial derivative. These are momentum, energy, mass conservation laws, and also the state equation. And these are computation domains. We computed the area within surrounded by the red lines, which shows the computation domain, the experimental visualization window, which we can take pictures after the collision of jets, the reaction chamber, and the end of the side passages, or the passage for the jets to collide at the middle of the chamber. The number of grid points we used is about 41 million. And the computations are conducted for the same geometry and same conditions as shock tube experiments, which I explain later. And also the boundary condition downstream is given by the Thomson non-reflection condition, otherwise known as the method of line. So next, this is details on the experiment device we used to measure the pressure increase near the collision point of jets. We used about a 9-meter long shock tube in order to generate high-speed jet flow having a strong shock wave. In the low-pressure chamber of this shock tube, we installed a device which is made of the reaction chamber and the side passages. We call them side passages, but they are passages in which the super multijets are flowing in to collide at the center of the reaction chamber. Near the collision point of the reaction chamber, we installed a pressure sensor, which is highly responsive. It's made by Kistler Instruments. And also, in the downstream part of the compression device, there is an observation window for taking Schlieren photography, which the pictures we took I showed in my previous presentation. So this is comparison of the flow field for computation and experiment. These 3 pictures, surrounded by the blue lines, are computation results. This is pressure distribution, this is streamline, and this one is computational density variation with a secondary processing based on Schlieren photography. This picture surrounded by orange lines is actual Schlieren photography taken by experiment. As you can see, the position of the shock front, which can be shown here, and also the size of upstream mushroom vortex area show good agreement between computation and experiment. I will also show comparison of flow field for 2 time periods, one earlier and one later. You can see that for both time periods, the position of the shock front and also the size of the upstream mushroom vortex area show fairly good agreement for both time periods. Again, emphasis is placed on the fact that both the computational and experimental flows show axial symmetry after the super multi-jets collide on the center axis, which may indicate stable compression due to collision of jets. So next we investigated the pressure increase of jets that collide at 90 degrees, in which the side passage is made relatively thicker. And we used the same device for the combustion experiment I showed in my previous presentation. This photograph is taken around the reaction chamber exit. And as I told in my previous presentation, strong light due to combustion occurrence can be observed. So this is in the prototype engine we used for combustion experiment. This is the same diagram I showed in my previous presentation. The 14 jets enter through the intake. They are made pulse jets by this rotary plate valve, which is installed in the middle. And a fuel injection device is placed downstream. And the pulse jets collide at the center of the reaction chamber. The engine mount can move freely to the right and left, and a load sensor is installed on the engine mount to measure thrust in the combustion experiment. So next are experiment results, and also this time computation results of the pressure increase obtained near the collision point of 14 jets. As you can see, for both experiment and computation, the maximum pressure increased to over 700 kilopascal, which is approximately 18 times that of the initial chamber pressure. This high pressure increase in intake was seen for both experiment and computation. And I'd also like to say again that experiment result was repeatedly or reliably obtained, with the maximum pressure value varying within less than 3%. We also did experiments where we varied the position of the pressure sensor, and we got similar results, and we also got results that implied the stability of the collision of jets. So to summarize up to this point, unsteady three-dimensional supercomputer simulations based on the CIP method and the biscales method applied for the stochastic compressible Navier-Stokes equation and theoretical considerations show that for 14 focusing air jets colliding with pulse induced by initial outer and inner pressures of 0.31 megapascal and 0.4 megapascal with the size of DD ratio 2.7. Pressure ratio at the chamber center without reactions is about 18, which agrees with experimental value. The simulation model is valid by using lots of experimental data. As shown in the other presentation by us, which I gave earlier, chemical reaction and high thermal efficiency are possible. However, weak nuclear reaction may be impossible because compression level may not be enough for the collision of 14 jets on the same plane. For occurrence of weak cold fusion, the number of jets is increased to 26, which is under development. Half of the spherical surface of the reaction chamber is for super multi-jets, which is shown here in this pinkish color, while the other remaining half can be used for exhaust. Therefore, we'd like to point out this geometry implies an open system. So next I'll explain the first scenario type that I've explained earlier, which is single focusing collision of hydrogen or deuterium and palladium injected into atmospheric chamber. And these are results of the supercomputer simulations. For basic scenario type 1, we obtained the maximum pressure over 200 megapascal and the maximum temperature over 3000 Kelvin. And these are time histories of the pressure distribution and temperature distribution at the center of the reaction chamber. This shows the time history of the pressure and temperature at the collision point. So for the basic scenario type 1, the single focusing collision of H2 or D2 in palladium injected into atmospheric chamber leads to over 200 megapascal and over 3000 Kelvin around the chamber center. However, if the compression is not enough for weak cold fusion, we next propose basic scenario type 2, which is single focusing collision of H2 or D2 in palladium injected into initially heated chamber of about 1,500 Kelvin. And these are computation results for the next scenario. In this computation result is the single focusing collision for a initially heated chamber of 1,500 Kelvin. As you can see, the maximum pressure at the collision point is over 70 megapascal, whereas the maximum temperature is over 6,000 Kelvin, much higher than the scenario type 1. And next, these are the temperature and pressure histories at the collision point. And next is a movie for the pressure distribution. I'm sorry, the temperature distribution for basic scenario type 2. Okay, so this shows a movie, and the jets collide at the center. You can see a red spot in the center, which shows temperatures over 6,000 Kelvin. Okay, so to summarize, for basic scenario type 2, which is injecting the single focusing collision of H2 or D2 and palladium injected into initially heated chamber of 1,500 K, leads to over pressures of 50 megapascal and over 6,500 Kelvin around chamber center for occurring stable weak cold fusion. However, in order to prepare initial heat of 1,500 Kelvin, another energy source is necessary. Therefore, we next propose scenario type 3, which is a combination of basic scenario type 2 after basic scenario type 1. So these are results I previously showed, basic scenario type 1. And as you can see, after the focusing collision of jets, the temperature near the chamber center is increased to over 1,000 Kelvin. So after this scenario type 1, we do scenario type 2. And these are conclusions and outlook for my presentation. First, I showed basic scenario type 1, which is single focusing collision of H2 or D2 palladium injected into atmospheric chamber, which leads to pressure over 200 megapascal and over 3,000 Kelvin around the chamber center. However, if the compression level is not enough for weak cold fusion, in this case, we involve type 2, single focusing collision of H2 or D2 palladium injected into heated chamber of about 1,500 Kelvin, which leads to pressure over 15 megapascal and temperature over 6,500 Kelvin around the chamber center for occurring stable weak cold fusion. And in order to prepare initial heat of 1,500 Kelvin, another energy source is necessary. Therefore, we propose scenario type 3, which is double focusing collision of H2O2 at first stage injected into atmospheric chamber, and also H2D2, vapor H2O, and palladium injected at the second stage, which leads to over 50 megapascal and temperature over 6,000 Kelvin, without another energy source for heating initially the chamber to 1,500 Kelvin. This scenario type 3 is close to basic scenario type 2, added after scenario type 1, because high temperature of vapor H2O by chemical reaction occurring after scenario 1 remains around the chamber center, whereas high pressure region generated by scenario 1 expands very soon with sound speed, which results in low pressure. Thus, after power by scenario 1 is extracted, temperature at 1,500 Kelvin and 0.1 megapascal is possible around the chamber center. Therefore, we can do scenario 2 after scenario type 1. So this is the same material I presented in my previous presentation. This is the same diagram I showed in my previous presentation. I'd like to point out that the stability of the jets, this is a picture of the flow field after collision, doesn't change that much, even if we add disturbance to the inflow of the jets. And also, the pressure increase near the collision point when disturbance is added is not disturbed much, although the variation is slightly larger than without disturbance. The maximum pressure is increased to nearly the same value as without disturbance. And again, I'd like to show the 5 physical reasons why we think the collision of super multi-jets is stable. Although quantitative research about the stability of these jets are still undergoing, we are thinking of numerous reasons why the collision of jets is stable. First of all is that the phenomenon may be stable by nature. When the center jet is slightly inclined to an upper angle, the upper part around the collision point becomes higher pressure, resulting in a force towards the lower pressure area, resulting in the inclined jet to return to a horizontal angle. And the second reason, as I explained, is that this collision is mainly produced by collision of very thin spherical shock fronts generated stably and repeatedly. This is computation result just before the collision of the shock front. And I'd like to point out that this is spherical shock fronts. It's different than two-dimensional shock fronts. And also for point 3, the jets coming after the shock fronts are in laminar flow, because these are pulsed flows, which are potential flows, as is well known from fluid dynamics textbooks. And the fourth point is that, well, this is a computation result for a single jet injected into ambient pressure chamber. And you can see that before the turbulence occurs, there is a certain length where the jet flows in a straight direction. And this length is over 2.0, which is a characteristic of jets that is shown in several textbooks. On the other hand, the smallest R/D ratio shown in this research is about 1.35. Thus, the condition similar to nearly laminar straight jets will also lead to stable collision of the super multi-jets. And the fifth reason is that there's less shear stress between the jets, because there's very little stagnant region between the neighboring jets. This fact will lead to nearly laminar flow, whereas the computation of a single high-speed jet, in this picture, this is for the super multi-jets and very, very less stagnated area on the collision point of super multi-jets. You can see that for the single jet, it has strong shear stress around the contact surface between the jet and the ambient air, which cannot be seen in the computation for super multi-jets. And that's the end of my presentation. Thank you for listening.
Thank you very much, Konagaya, for an excellent presentation. And it's cool, and super multi-jet sounds awesome. So just on the nomenclature, it's fantastic. You're talking about trying to raise temperature, and I believe that raising the temperature is important, and you're looking at alternative ways to raise the temperature in the core, I guess. Have you considered using atomic hydrogen and producing that and immediately injecting it? Or alternatively, working with Dr. Roshin Umaza, who lives in Tokyo, and he has a gas that has been analyzed by one of the universities in Tokyo to apparently to stably store a small percentage of atomic hydrogen. And then you're benefiting from the recombination 4.48 EV in the center. And he's also been able to burn carbon dioxide with the gas. And so you don't have to use palladium, which I think it's going to get expensive after a while if you have a car burning palladium. And so there's just some points where you might be able to take this, and I can connect you if you like. And then secondly, just a by-the-by question, is it based on a sort of engineered collapse of a cavitation bubble?
Okay, so to sort out your question, you said, is it related to the collapse of a bubble?
Are you trying to basically engineer a collapse of a cavitation bubble?
Yeah, good question. We are thinking about it. Yeah, of course. Yeah.
Okay.
In the automobile application? Yeah, you made say on the cost, but at first we want to apply to the aerospace target, maybe, I don't know. But of course, we also try to automobile application. First is combustion without cooling system. Yeah, very high thermal efficiency will be obtained. That's the first target.
Chilani.
So if I well understood, you are using atomic hydrogen process. So to make atomic hydrogen, the best material is Constantan, because it's about 8 times more efficient in respect to palladium, and the cost is about 1,000 less. So I would like to suggest to explore this other material. You can make a nano Constantan, and so the problem of a cost will be solved easily. just my suggestion. Thank you.
Yeah. Okay. Thank you for your very kind presentation. And from what I heard and what I understood, you showed that the 26 injector reactor is some kind of 3D structure. Okay, it's a spatial structure. And as a mineral chemist, zeolitic structure have been used, and some palladium nanoparticles or nanoclusters have been incarcerated in zeolitic spaces, okay, cavities. Okay. So my question is, could the collision point that you are able to produce with this 3D structured reactor could mimic in some way the cavities of zeolitic structure, transient equivalent of what can be built with zeolitic structures? This is my question.
Yeah, maybe your question is related to the spatial distribution of palladium or something, maybe? Supply of palladium.
To what I understood that you use palladium nanoparticles in your fuel reactor. And in the case of zeolitic structure, they also tried to incarcerate palladium clusters in zeolitic cavities. So I just make the link, but maybe it's wrong, but I just made the link between these two different approaches. One is mineral approach, with a continuous presence of palladium clusters in a mineral cavity that some people succeed to build in these cavities. And your approach, which is, to my point of view, but maybe I'm wrong, a quite different approach where there is a collision point, and at that point, I guess that there is palladium nanoparticles that are also expressing some kind of what you call cold fusion reaction.
Yeah,
so is there a link between these two fields?
Different field, but I worked for Nissan Motor Company during the 10 years. And at that time, the liquid fuel particles distribution we optimized. So I have many know-how to control, optimize the fuel distribution, particle distribution. So of course we have numerical code, original numerical code to evaluate the particle distributions. So good question. We are trying to optimize the distribution of particles. Okay.
Give the last question of the session to Dr. Uemura.
Nice presentation, Konagaya-san. I have a question. Why did you add nitrogen gas to induce cold fusion? What is this?
Okay.
Please tell me.
The reason why we wrote in many slides nitrogen may be added is because we haven't, the computations we showed in this presentation is for the collision of air. And we haven't done it for collision of hydrogen yet, which is undergoing right now.
Okay.
Yeah,
that's why.
that's why.
Okay, thank you.
Another reason is safety, for safety. Yeah.
For safety, you add
I am afraid on the very big energy occurrence.
Okay.
Yeah, so
thank you.
We want to control by changing the N2 ratios.
Okay, thank you.
Thank you.
Thank you very much, and thank all of the speakers this morning.